This is part 3 of the Module 10 lecture recording. In this section, we're going to talk about the example we started this section with, and that's of the plant geneticist that raises 250 independently progeny of plants under identical conditions from a cross that is hypothesized to result in a ratio of colors of flowers of 9 to 3 to 3 to 1, and that is from amber to orange to yellow to green flowers of these marigold plants. The observed frequencies are given here. So from these 250, 152 had an amber color, 39 had an orange color, 53 have yellow color, and 6 had green color. So we want to test the hypothesis that the population proportion, so the colors, is in fact 9 to 3 to 3 to 1 at a significant level of 0.05. All right. So we're going to follow our familiar hypothesis test procedure. We're going to state first the null hypothesis, and then select the distribution to use, calculate the test statistic, and either using the p-value or the critical value, we make a decision about the null hypothesis, and we conclude with interpreting our decision about the null hypothesis. All right, so in the first step, the hypothesis is, as we discussed previously, that under the null hypothesis is that the probability of success of the first color is 9/16, and the probability of the second color is 3/16, and the third color is 3/16, and the green color is 1/16. And of course, the alternative hypothesis that at least one of these probabilities does not match to the probabilities we're assuming. And remember, in the problem we have the 9 to 3 to 3 to 1, and we change it into a probability by summing these numbers to 16, and then we divide each of them by 16, so that these probabilities add to 1. So be careful here. In these problems, sometimes we're not given the probabilities straight out. We need to find them out, like in this example. Now, again, as we said, this is always a right-tail test, and the significance level for this problem is 0.05. All right, what distribution should we use to solve this problem? Well, you see first that this is in fact a multinomial experiment, as we discussed it before. And then see, we have 4 outcomes, and then we have the individual probabilities add to 1. Then the second condition is that all expected counts should be at least 5. And to get the expected counts, we use the probabilities that we assume under the null hypothesis is 9/16, 3/16, 3/16, and 1/16. And we multiply them by 250 because there were 250 trials, plants in this case. So you multiply 250 times each of these probabilities, and then you find the expected values. And you can see that every expected value is larger than 5. So we meet the two conditions. One, we have a multinomial experiment, and then all the expected values are larger than 5. So then we're justified in using the chi-square distribution with degrees of freedom equal to the number of categories minus 1. So there are 4 categories minus 1, so the degrees of freedom is 3. All right, so now we know what distribution we're going to use. The next step is to calculate the test statistic. A suggestion I have is to avoid mistakes in these calculations, because you can see it's a long calculation, is to create a little table on the side where you summarize the observed values and the expected values. So then to find the test statistic, so you take the first observed value minus the first expected value, you square that quantity and divide it by the first expected value. Then you find the observed value for the second category, and then subtract the expected value for the second category, square it, and divide it by the expected value. Then you go with the next category. You find the observed value of that category 3, 53, minus the expected value of that category, 47.875. You square that and divide by the expected value, and you do the same thing for the last category. Observed value minus expected value squared divided by the expected value. If you carry out each of these calculations, you find these values right here, and then you sum them, and then you end up with the chi-square test statistic. Now notice that each of these values is called the individual chi-square contribution to the large chi-square, the test statistic. So here you can see that this chi-square component, 5.929, is much larger than the other components. All right, so now we have the test statistic. The next step is we need to make a decision about the null hypothesis. But first we need to find, if you decide to use the critical value approach, or if you've been asked to follow that approach, the first step is to find the critical value of the chi-square so that you can determine where the rejection region is. So in table 6, you look for row on the first column for the row with 3 degrees of freedom. Then go across and look at the probability at the top, 0.05. Then you will find at the intersection of this column and this row that critical value, which is 7.815. So the rejection region is that the chi-square value should be, if it is larger than 7.815, you will reject the null hypothesis. And here, of course, I'm referring to the value of the test statistic. If you decide to use the p-value approach, then you look at the calculated value of the test statistic. Then in table 6, look at the row for 3 degrees of freedom and see where this value is with respect to the values listed there. And you will see that 8.972 is between 7.815 and 9.348. And this corresponds to the probabilities of 0.05 and 0.025. So from here, then you see, and because these are probabilities on the right side, then you can see that the p-value is between 0.05 and 0.025. If you have access to Excel and you would like to find out the exact p-value, well, here's the formula. So use this chi-square.dist.rt with the value of the chi-square that we calculated, and then the 3 degrees of freedom. And you find that the exact p-value is 0.0297. All right, with this information, then we move on to the 5th step, where we make a decision about the null hypothesis. And you find that the calculated value of the test statistic at 8.972 is larger than the critical value, 7.815, which is telling you that the calculated value of the test statistic is in the rejection region. Also, the p-value is smaller than 0.05, so both approaches are telling you that we should reject the null hypothesis. So we're rejecting the hypothesis that the actual proportions or the actual probability of success of each color does not match what the geneticist is proposing. So the interpretation of this decision would be that at a significance level of 0.05, we can conclude that the frequency of the colors of the flowers from the progeny does not match the expected ratio of 9.331. And being more specifically, it doesn't match at least one of the hypothesized probabilities of success. So you could also say it that way. All right, so often these problems, when you're doing a goodness of fit test, it gives you with the lingering question, well, which category is not matching the expected ratio? An empirical approach that is easy to do, this graph is created with Excel, and then you can, while comparing to this, you see, and this is comparing the observed versus the expected values. So the orange columns are the expected values, and these blue columns represent the observed values. And here you see that they don't match exactly, but they are relatively close, except for the green color. And now in this table, we're listing the contributions to the overall chi-square value. And as we mentioned earlier, the largest chi-square is for the green color. And so the green it appears to be the category that does not match the expected probability of success, because the observed number of green plants with green flowers is smaller, significantly smaller, or at least appears to be significantly smaller than what we expect. All right, so again, I'm not going to ask you to do this, but this is the natural sequence from this type of test to investigate where the discrepancy is, or rather what discrepancy is causing the null hypothesis to be rejected. And of course, knowing this, it will help the geneticist to evaluate how he did his crossing of the plants. All right, so we'll stop here. This is the example for a goodness of fit test. And this is one example which is different from the one in the textbook. So between the example in the textbook and this example, you have two examples that you can use as reference to see how these problems are, how you can use the 5-step process to perform a goodness of fit test. All right, in the next section, we'll talk about the test for independence and homogeneity.